If a gain k is part of the g term, you would expect which of the following to happen? What does it mean it's part of the g term? I think what it means, let me think. So let's draw a sketch of a feedback system. So here we would have an input going in and something measuring the error. So the input is going to be theta ref. Okay, so that's the reference. Theta is the pitch. So we use theta for pitch in aircraft. And that's the reference that your system is using. Then you could have your K amp here. And then you would have what? You would have maybe a function like, I don't know, s plus 1 over s plus 3. And then maybe you'd have a position output, which would be put over here. Then you'd have some h function, and then you'd go back here. And this would happen again and again, and this would measure the difference between what you're getting here and what you inputted originally. Okay, so if I have k amp here, essentially, what is your what you would expect to happen, the input to the root locus program would be g times h, where h doesn't have k. Well, k is not in h in the first place, because h asterisk mean h with k taken out, but there is no k here. So the input to the root locus would have to be g asterisk h, because this is our g. Let me make that clear. This is our g, and this includes k. And k is what we want to vary in the root locus. That's why we don't want to input it in it. Okay, so it's definitely not the first one. Definitely not this one. The closed loop transfer function characteristic equation would not be dependent on the value of k. Well, that actually isn't true, because the closed loop transfer function would be given by g over 1 plus gh, and there's a k in here, and there's a k in here. So it would definitely affect the value of the closed loop transfer function. The closed loop transfer function poles would change as a function of k. So let's see, the poles are the bottom. Would they change as a function of k? I don't think they would. The zeros would change. The poles wouldn't, because we're multiplying k with the numerators and not the denominators. So I would say none of the above. However, the book gives solutions for C. So I'll circle back on that one. Let's look at 8.5. A pole of the control loop transfer function will be found to be 0. A pole of the control loop, a pole of the closed loop transfer function will be found to be a 0 of the 1 plus gh term. Well, 1 plus gh is in the denominator. So everything that makes the denominator 0 is a pole. And so it would be a 0 of this, yes, because the definition of a pole is what makes the denominator 0. And this is an expression for the denominator. So that is definitely true. Which of the following depicts the transfer function for a servo actuator with a time constant of 0.2? Well, let's remember what a time constant is. It's 1 over the root So is the negative reciprocal of the root. So if the time constant is 0.2 seconds, then the root would be negative 1 over, well, let's say that 0.2 is 2 over 10. So this would be negative 5. And so if this is a root, then this means s is equal to negative 5, which means s plus 5 equals 0. And that leads us to this. Now, why do we have a 5 in the numerator as well? Because it's because of the Laplace transform, and because this comes from a servo actuator, which is delaying the response with an e to the 5t. And if you do the Laplace, this is what you get. And I'm sure there's like a deeper meaning than that, but that's what I can think of right now. I hope this was useful, and I'll see you next time.